No, that's Florida you're thinking of. There's no swamps in Alabama that I know of, but I never caught an alligator. But I did see one in Gainesville, Florida, just like hanging out in this park where everyone was like having lunch, a big old alligator, and it was just like hanging out, and I was like, I think I'll eat my lunch somewhere else. It was hanging out eating lunch. Okay. So last time, uh, we talked about the Voigt stress and the Voigt strain, and we said there was this relationship that if you write out all the strains in the Voigt form, so epsilon, xx, yy, zz, and then gamma, yz, gamma, xz, gamma, nope, y, is equal to a 6x6 compliance matrix. And I haven't talked about how to get these values yet, times the Voigt stress. So that's xx, yy, zz. You can keep writing those as sigmas, or you can write them as taus for the shear stresses. So yz, xz, xy. And so I'll call the compliance matrix C. And it's also another way to think about this relationship is that sigma xx, yy, zz, and then the taus, yz, xz, xy is equal to the 6x6 stiffness matrix. I'll call that the matrix S times the strains xx, yy, zz, and then the gammas yz, xz, xy, where the compliance matrix and the stiffness matrix are inverses of each other. So this is the same thing as saying the stiffness matrix is the compliance matrix inverse. Okay, so if we can come up with the values for that matrix, then finding either the state of stress or the state of strain is enough to figure out the other one. I know what I was going to say. You can remember, so which one of these is the compliance and which one is the stiffness? If you're, so say, okay, it's easy to tell if you're looking right at this thing that says it, you know. But what if you know the stresses and you want to calculate the strains? How can you like refresh your memory about that? You have to use the compliance matrix for that. The materials we're using are stiff. They're engineering materials. They're not easily deformable, you know, like macroscopic amounts. And so you would expect the values of the compliance matrix for engineering materials to be very small, and you'd expect the elements of the stiffness matrix to be really big. And you know that stress values are going to be big. In order to get any kind of deformation, you have to put a big load on on steel or whatever. So these are going to be big, and the strains are going to be small. The deformations are going to be small. So you know, if you're starting with something big and you're ending with something small, you know those have to be small. And here, if you're starting with something small, way smaller than 1, and ending with something way bigger than 1, these have to be big. And so compliance stiffness. Okay, so what this says is that we just need the 6 by 6 is 36 values. That describe our material, whatever material. And that means that you have to do 36 mechanical tests to measure your material. I've never tried to draw this before, but this is supposed to be like that crying guy emoji. What? All right, well, no, wait. For the materials that we're interested in, the materials that these engineering materials, the materials that we're addressing in this class, those 36 values can all be expressed in terms of 2 parameters. And actually 2 easily measured parameters. Those are capital E, which is called the Young's modulus, or just the stiffness, or the modulus of elasticity. Yeah, it's like the Huff Daddy of parameters. And then the other one is lowercase Greek letter nu, looks like a scripty V, and that is Poisson's ratio. Or in English, the fish ratio, but it's actually someone's name. Okay, so let's talk about calculating those. You get these from a pencil test. Okay, so let's talk about a tensile test and how you calculate these things. So a tensile test, company that's best known for making machines that do tensile tests is MTS, a metro area Twin Cities company. But the way it works is you have a clamp at the top, and a clamp at the bottom. And inside the clamp, you put a sample of the material that you're interested in. And then you just pull it apart. You apply some known force, so you're measuring that force. And we're going to assume that we're using a coordinate system where the x-axis is along the long axis of the sample. So here's the x-axis, here's the y-axis. And you just measure the load and deformation as the tension is applied. Then the definition of the Young's modulus is the normal stress along the x-axis, so stress xx divided by strain xx. It's basically the spring constant. You're dealing with steel or something, so it's going to be gigantic. And the units are force per area, so pascals in SI units. And then the Poisson's ratio is the negative strain in the not Poisson's ratio. So negative strain in along either one of the off axes, so strain YY or strain ZZ, divided by the strain in the direction, the normal strain in the direction of the load. So this, or you get the same answer if you do epsilon ZZ over strain XX. And since that's a strain divided by a strain, that's unitless. Just a number. Okay, so if you're loading this thing along the x-axis, so this idea makes sense. That's works exactly the same as a spring constant. But this one looks a little weird. Like, why would there be any? We're not doing anything in the y or the z direction. Why would there be any strain in the direction of the y-axis or the z-axis that in this case would be coming out of the page? Well, the way any elastic material works is if you stretch it this way, you get a contraction this way and this way. And if you compress it, you get a bulging out this way and this way. So the total volume of the material is not going to be conserved in most cases, but the off axes are going to do whatever they have to do to make it a little closer to conserved. Okay, how much they bulge out or contract in is determined by what material you have. So Poisson's ratio values range from 0 to 0.5. 0 would be if you stretch it and it stays exactly the same thickness in the other two axes. And 0.5 would be if the volume is conserved. So that's called an incompressible material. If you ever don't know the Poisson's ratio of a metal, most metals have Poisson's ratio around 0.3. What? 0 just means that the thickness in the off axes is unaffected by the stretching or compression. And actually, there's one material that if you do this test on, sort of a common material, that does have basically 0 Poisson's ratio, and it makes sense if you think about the way it's used. Cork. If you do a tensile test on cork, you stretch it, it doesn't change thickness at all. If you compress it, it doesn't change thickness, which is why corks are used traditionally in wine bottles, because if you put a cork in a glass bottle and pound on it with a hammer, compress it, you don't want that thing to bulge out or it's going to break the bottle. So cork is an example of a material with 0 Poisson's ratio. Once you know the Young's modulus and the Poisson's ratio for a material, the compliance matrix has the following form. The first row is 1 over E, negative nu over E, negative nu over E, and 0, 0, 0. The second row is negative nu over E, 1 over E, negative nu over E, 0, 0, 0. The third row is, what's the third row? It's a pattern. Yeah, negative, it's, yep, nu over E, negative, yep, 1 over E, perfect. And then 0, 0, 0. And those are the ones that give relationships between the normal stresses and the normal strains. Now we're getting to the rows that determine the relationship between the shear stresses and the shear strains. And so those have the zeros here, 0, 0, 0. And then 2 times the quantity 1 plus nu over E, 0, 0. And then the same thing with that 1 non-zero value moved over to the fifth column, 2 times 1 plus nu over E, 0. And then 0, 0, 0, 0, 0, 2 times the quantity 1 plus nu over E. And one of the things you definitely want to get in your calculator is there's a program listed, code for a program that's listed on D2L where you just give it as arguments E and nu, and it spits out this thing. You don't want to you're going to use this matrix a lot, and you don't want to have to type in 36 separate values each time. Okay. Okay, so that is the relationship between stress and strain. Well, this is if you have the stress and you want to calculate the strain. If you have the strain and you want to calculate the stress, just have your calculator invert this matrix. So now, before we start doing examples with certain materials and stuff, I want to talk about what cases. So basically, all of the things that we're going to do in this class are relevant for materials and loading environments where we're making these 4 assumptions. So these are the 4, I think it's 4. Yes. Assumptions we make in this class. And I guarantee this is going to be on a quiz. So pay attention to this one. First, small material deformations. Yes. It wasn't supposed to be today, was it? I don't know. Okay. I just kind of... Small material deformations. So we're talking about less than 0.01% elongation or compression. If it's visible at all, it's not very visible. You know, we're not talking about taking a meter-long bar and stretching it an inch or anything like that. Just small, tiny deformations. The second assumption we're making is that there's a linear relationship between stress and strain. That linear relationship is that relationship that says the strain is equal to the compliance matrix times the stress. Okay. So just generally an equation like this means that there is a linear relationship. If you're multiplying a vector times the matrix with constant values and you're getting another vector out, those 2 vectors have linear relationship. That's why they call that linear algebra. The stuff with the matrices. That's also called Hooke's law. And then the third assumption is that the materials are homogeneous. Homogeneous means if you go from one point to another point in the material, you see the same material at both of those 2 places. Like when you homogenize milk, you take, like, if once you get the milk out of the cow and you take a sip and there's like a glob of fat and like a glob of blood and like, hair, all this stuff. But then you homogenize it and every sip is like the same consistency. You have every sip has a little bit of blood, a little bit of no, I don't even go there. Yes. So homogeneous materials mean the material is the same, or the material has the same properties at any 2 points. when our oldest kid was like, I mean, really young, like 3, like he could barely talk, and we were out to breakfast with my sister who doesn't have any kids, and she's like, they brought milk for my kid, and my sister's like, Jack, do you know what kind of animal milk comes from? And he's like, any mammal. It was really funny. And she's like, oh, well, that's correct. And she's like, well, what kind of mammal do you like the milk from? And he's like, whale. And properties at any 2 points. And then the last one is similar but not the same, so make sure you understand what this distinction is. Isotropic materials. Isotropic materials mean, so homogeneous means you go from one point to another and you have same material there. Isotropic means at a single point, no matter what direction you look in, the material acts the same. So there's no preferred direction, like it's stronger if you load it along this axis, weaker if you load it along this axis. So the material properties are the same in any direction, but think of that as being at a single point in the material. Okay, so Young's modulus and Poisson's ratio are only defined, are only meaningful for isotropic materials. So that's an important one for us. If you can't assume the properties are going to be the same in every direction, then you're going to have more complicated forms for those 36 values in the compliance and stiffness matrix. And correspondingly, you're going to have to do more tests to figure out those material properties. Of a non-isotropic material. So any metal, so you can make metals that behave differently in different directions, but you just have to very carefully, very slowly grow the crystal lattice in a single direction. The reason a hunk of steel behaves the same way in any direction is because you have all these crystals pointing in all these different directions, and they sort of average out, Cork, probably, but I don't know that for sure. But definitely wood. What? Really? Oh, okay. Yeah, so definitely anything with a grain is non-isotropic. Bone in animals is non-isotropic. Bones aren't made to be very strong if you're compressing them from the side, but they're really strong in compression lengthwise. So what that means is if you took a piece of bone and did a tensile test along the long axis of the bone, you'd get certain stiffness properties. And if you turned it around and did a tensile test in the other direction, it would look like a totally different material.
Is that non or isotropic?
That would be non-isotropic. So the materials that we're talking about, if you have a piece of metal and you form a sample, let's say a long. No, the things we're doing are not going to be very relevant for wood or bone. There's sometimes you could do it, use it in sort of a limited way, but for the most part, this stuff is useful for concrete and metals, and in those things, no matter what direction you tested it, you'd get the same answers, and so those are isotropic.
Would it be the same for like sedimentary rocks?
I don't know. Do they, because they...
Well, the patterns are kind of like.
Mhm. Yeah, I would guess so. I mean, I think if there's any kind of visible grain, that it's likely that it's not isotropic. And it's probably also true that there are a lot of things that are not totally isotropic, but you know how, like in circuits, you can do these calculations, yeah, from with like pretty amazing precision. You know, like the answers you get are exactly the answers that you would get if you took a measurement. Deform and any kind of mechanics, like the mechanics of failure, continuum mechanics and finite elements, like you're pretty happy if you can just get a reasonably good ballpark number, you know, to within, if your answers are within 10 or 20%, you're happy, you know. So so there are cases where you have non-isotropic materials, but that non-isotropy is only within a few degree, you know, few percent or whatever, and you're just like, sure, it's so much easier to deal with, treat it like it's isotropic, that I'm just gonna assume it's isotropic, do the tests, and then I'm gonna give myself a little bit of extra cushion with the, you know, margin of safety on whatever I'm building, you know. So let's do a example of a tensile test. What you would get out of the measurements and how you would put that into your compliance matrix. So let's say you have a sample like this. It's a long, skinny rectangle. The dimension this way is 2 centimeters, 0.02 meters before the deformation. And the thickness this way is 1 centimeter. And the height is 10 centimeters, so 0.1 meters. And we're going to apply tension to the two ends. So after the deformation, we measure the length. So let's call this one the length. Let's call this one the width. And this one we'll just leave out of it for now. So after the deformation, length is 1 point, I got 3 zeros there, 0, 0, 0, 3. No, that would be too much. 0.10003 meters. And the width, that'd be bigger or smaller than the undeformed value? Smaller. So let's say that's 0.009. 2 more 9s and a 2 meters. And we want to find the Young's modulus and the Poisson's ratio. Well, Young's modulus is equal to the normal stress along the load divided by the normal strain along the load. I'm going to draw the coordinate system that I'm using. So the x-axis would be like this. Bless you. The y-axis would be like this. The z-axis would be like that. So first calculate the stress. So the xx stress is equal to the deformed length along the loaded axis. So 0.10003 minus the length before the deformation, 0.1, divided by the length before the deformation, 0.1. And you get the value of, oh, and I need to give a force too, 5,000 newtons. So this, what I'm saying here is totally wrong. I'm thinking of the strain. So the XX strain is this. And that is 3 times 10 to the minus 4. That's a strain, so it doesn't have units. And then the stress is the force divided by the area. So that's 5,000 divided by the area is 0.01 times 0.02. So the area that we're talking about is, think of what's the area that's determining how well this material resists that stretching. You know what I mean? If this was twice as long, that wouldn't have any effect on how well this material resisted those 5,000 Newton forces. But if we like doubled the thickness, that material would resist that deformation more easily. So the area we want is like the cross-sectional area that's, I guess, perpendicular to the loading direction. Yes, that's right. So that's the area of the face normal to the force. And that gives you 2.5 times 10 to the 7th pascals. What about plus or minus? Should that normal stress be positive or negative? Positive. Tension is always positive and compression is always negative. And the strain, that sign works out on its own. So now we can calculate the Young's modulus. Young's modulus is equal to 2.5 times 10 to the 7 divided by 3 times 10 to the minus 4. You get this really big value, and this is about the size that we're going to see. 8.3 repeating times 10 to the 10 pascals. Or 83.3 repeating gigapascals. And for Poisson's ratio now, Poisson's ratio is the negative of the off-axis strain, so epsilon YY, divided by the on-axis strain, so that's epsilon XX. We already have epsilon XX, so we have to calculate YY. That's equal to the deformed length parallel to the y-axis, which is 0.00, and then let's do this. I think I'm going to need that 9 later. There's a 9 on the second page that isn't in this one, but let's put another 9 in here. I think otherwise we're going to get something that's impossible. Okay, so W has 4 9s and then a 2. And so now here we have 0.0099992 minus 0.01 divided by 0.01. You get negative 8.0 times 10 to the minus 5th. So now Poisson's ratio is equal to the negative of negative 8.0 times 10 to the minus 5th divided by 3.0 times 10 to the minus 4th. And you get a Poisson's ratio of 0.26 repeating. And those values are, for Poisson's ratio and Young's modulus, are both pretty much in the ballpark of values that you would see for metals. So I had to change this to 4 9s because if it was only 3 9s, here we get a value of negative 8 times 10 to the minus 4th. And then we do this and get a value of 2.6 repeating. And a value of 2.6 repeating is not in the realm of possibility. What that would mean is if you stretch it, it expands out to the side. And if you compress it, it compresses on the sides. That would be very weird.
That'd be awesome.
Yeah, I'm sure you could use that for some kind of perpetual motion machine if you thought about it for a while, but unfortunately you can't find materials like that. Yeah, exactly. Okay, well, so now you take those values, put them into the compliance matrix, and then problems like you've done in the homework with stress tensors so far, get a stress tensor, put it in the Voigt form, multiply it by the compliance matrix, and you can figure out what the deformation is for a given stress. Anybody have any questions? Okay, let's stop there, and then on Monday, we'll talk about stress transformations, which is, so you can use a rotation matrix to, so if you have a vector represented in one coordinate system, okay, so this vector in one coordinate system is 1, 0, 0, okay? How do you represent that in a coordinate system that's rotated 35 degrees from that one? Well, you can do it with a rotation matrix. And, I said that what defines a vector is the relationship between the measured values and how those values would be measured in a different coordinate system. And it involves the rotation matrix. The same thing is true of tensors, and stress is a tensor. So now we're going to next talk about how to use rotation matrices to represent stress tensors in new coordinate systems. And that's stress transformations. Okay. See you later.